So in the previous derivations, optimum headway is given by this formula. However, this is an ideal case where we do not consider any constraint on this headway. In reality, we send a truck to ship our goods. So typically, the truck is with certain capacity constraint. For example, the truck can ship at most 100 gallons per time. So that indicates we have a max load equals to 100 gallons per time. So then the issue is that if we want to ship a load which is larger than the max load, let's see, if we want to ship 300 gallon milk each time. So what will happen? That means we need to have multiple trucks. So this equals to 300 gallon divided by 100 max load equals to 3 trucks. This will affect our transportation cost. Remember, we have our fixed cost, which is related to the stopping cost and the mileage cost. If you have a load which is higher than the max load of a truck, then you need to send multiple trucks. So the fixed cost will be multiplied by the number of trucks. So the total transportation cost will be adjusted based on the number of trucks. So in general case, the load each time we dispatch, which is d prime h. So let's see, we have a maximum load of the truck, CV max. Then the number of trucks will be the load we dispatched divided by max load. This may not be an integer, right? So if we do not have an integer, we will round it to the integer which is higher than this load. So for example, if we have a small load where the load is smaller than Vmax, then we need only one truck. So we need to put an equation here. Then if the load is higher than the max load, but is smaller than 2 max load, then we need 2 truck, and so on. So let's use Colab to show what will happen if we consider the capacity constraint. So first, let's adjust the cost function. Now we give another parameters, the max load, which is a Vmax. So the only things we need to adjust is the number of trucks. So this indicates we have hd prime divided by max load, and then round it up to the integer. We use this ceiling function in math, so we import this math package. And then after we do the calculation of number of trucks, then we will adjust the fixed cost by multiplying it with the number of trucks. Then this will give us the total cost under this capacity constraints. So to show the plot a little bit clearer, we adjust the number of possible headways from 12 months to each day. So now we have, like in the whole year of choices of headways, from like 10 days to a year over 10 days. The reason why I start from 10 days is because if the headway is too small, then the cost is too high, which is not easy to show in a figure. So under these settings, we consider 2 possible max load. One is 50, one is 100. So the first result we will show use the red color that indicates the cost curve under max load 50. And then a next curve, which is a blue curve, we will show the cost curve under the max load 100. So from the plot, we can see at the beginning, when the headway is very small, So that means the load each time we dispatch is always smaller than the max load. So in this case, the curve looks actually exactly the same without considering any capacity constraint. So the red curve and then the blue curve overlaps with each other. And then starting from around 0.15, this reached the max load 50. Then you can see there's a huge jump in the cost for the red curve because it's reached the capacity and then the second truck is dispatched. And then you can see the next turning point where the max load is 100. So at this point, the blue curve shows that the load is over the maximum capacity, and then a second truck is used for the blue curve. And then because the max load is 50 for the red curve, so the third truck is used. So for the blue curve, this is a second truck. For the red curve, this is a third truck. So and so on, we can just label a number of trucks for different load capacity. So with this observation, you can see when the max load is big enough, the minimum cost is still achieved around 0.21, which is here. That's our optimum solution without considering the capacity constraints. But then when the capacity is small, for example, the capacity is 50, then 0.21 will not be the optimum solution because it needs to send the second truck. So in this figure, we can show the optimum solution for the cases where the Vmax is 50 should be this point. In fact, the decision maker should not dispatch the load larger than the capacity of the truck. Let's use the cumulative curve figure to illustrate why the decision maker should choose a small load. For example, let's assume the Vmax. So in this case, the current load is larger than 1 Vmax but smaller than 2 Vmax. So we need 2 trucks. Then we consider to adjust the decision. Let's just dispatch half load each time. Then each load is less than the Vmax. So the new headway is just the half of the previous headway. And load is also half of the original load. So in this sense, the load is smaller than Vmax. Each time we only need 1 truck. So after doing this adjustment, you can see the total number of trucks we need are the same. So for the 2 dispatches, we need 1 truck each time. And then for the dispatch with larger load, we need 2 trucks 1 time. So the number of trucks are the same. So let's see what the cost. Remember, we have the 4 cost terms: the run cost, the waiting cost, the fixed cost, and then the variable cost. So after we do this adjustment, the number of trucks changes from 2 to 1, and then the headway changes from h to half h. So that indicates the fixed costs remain constant. And then because our headway reduces to half, the run cost reduces, the waiting cost reduces, and then the variable cost remain the same. So finally, the total cost reduces. So that shows that if we adjust the decision from a load larger than Vmax into the load smaller than Vmax but break them into equal amount given the number of trucks, we can always find the total cost is reduced. That's why in the optimum solution, the decision maker should not choose a dispatch load larger than Vmax, because if it chooses a larger load than Vmax, you can always break it into smaller loads with the same number of trucks achieve a lower total cost. Hence, the optimization problem for the decision maker is trying to minimize its total cost per item, given that the load dispatches is smaller or equal to Vmax. So this is a constraint optimization. Recall that the shape of the total cost function is a Necki curve, and then the constraint can be written as the headway smaller or equal to a threshold. So we can decompose the problem into two cases based on this constraint. So case 1, if the truck capacity is large enough, let's see if this is a Vmax divided by the demand rate. And then our constraint tells us that we need to find optimum solution within this range. So this is exactly the same as our previous problem where we find optimum solution based on the first order condition. However, in the second case, if the capacity of the truck is small, then our optimization problem needs to find the solution within this range. So that indicates our optimum solution is bounded by the capacity. So in this sense, we can have the optimum solution under capacity constraint depends on two cases. So the first case is just a problem, just a solution determined by the first order condition or bounded by the capacity. So in short, we can get the minimum value of these two. So in our previous example, we have calculated the optimum solution given by the first order condition is 0.21. And then given the Vmax value, let's see if the Vmax is 50. So we can have bounded value for headway is 0.13. So if the Vmax value is 100, and then we can have the bounded value to be 0.26. So that indicates the two cases, right? So the first value here, 0.13, and then the second value here is 0.26. So that's why for the Vmax value, this is 50, and then this is 100. Yeah, that's why in the first case, where the Vmax is 50, the capacity does affect the decisions. So your optimum headway should be 0.13. And then the second case, where the Vmax is 100, which is large enough, so the capacity does not affect the decisions. The optimum solution is still given by the first order condition, which is 0.21.